Hello everyone, we are Group 1 and this is our video presentation for our capstone project, an autonomous surface vehicle for flood rescue operations. Our team members are Agam Saini, Divya Kapoor, Apoor Saxena, Priyam Gupta and Daksh Verma. We are fortunate to have worked under the guidance of our mentors, Dr. Satish Kumar Sharma, Dr. Neeraj Grover and Dr. Raja Raut. The increasing frequency and intensity of natural disasters highlight the urgent need for efficient search and rescue operations. Our team focuses on developing an advanced autonomous search and rescue boat designed to map its surroundings and locate stranded individuals in difficult aquatic conditions. Autonomous surface vehicles offer significant advantages in flood rescue operations, making them invaluable for assisting our NDRF teams. One key benefit is their enhanced accessibility and rapid response. ASVs can navigate through flooded areas that traditional rescue teams cannot reach due to factors like stream speed and water depth, ensuring quick assistance to stranded individuals without any human delay. Our ASV's engineering is based on three fundamental pillars: mechanical, electronic, and software.
Firstly, the mechanical aspect. We have chosen a catamaran hull design as the design offers the required stability and maneuverability with adequate payload capacity. The hulls were then designed on a software called MaxSurf, and the drawings for the hull are shown in the figure. The manufacturing process for the hulls included first assembling a skeleton structure made from wood and then giving it a body using aluminium sheets. The aluminium body is then waterproofed using silica gel and sealants like M-Seal. The two hulls were then connected using aluminium E-channels. Over the E-channels, an aluminium sheet is mounted again to make the base for the electronic components that are to be mounted on the ASV. A thruster for the motion of the ASV is then suspended below the hulls, connected to the base plate through a steering mechanism. The steering mechanism consists of a ball bearing, a linear actuator, and a rod that is suspended to be connected to the thruster.
So this is the simulation of our ASV which we are implementing for the search and rescue missions during the flood. So our ASV is equipped with all the sensors here also, such as IMU and LiDAR, for providing us with the data. And the platform which we are using is robot operating system, and this simulation is completed on the Gazebo software which we can see above. So right now our goal is to test whether our ASV model is stable in the water currents. So right now we are controlling it using the simple remote control operation through keyboard using WASD keys. As we can see, when we are pressing W, our ASV will move forward, and as we move S for stopping or reverse, we can see our ASV is moving backward. We can see that now we have released the keys, but still our ASV is being pushed backwards and forwards, which is due to the water currents present in the water, which is the physics of our engine. Further, we can see we can rotate our ASV in different directions, like roll, pitch and yaw. We can also control roll, pitch and yaw angles. So this is our IMU, which is inertial measurement unit. It is a combination of accelerometer and a gyroscope. The accelerometer provides us with the linear acceleration, and the gyroscope provides us with the angular rate, and together with these readings we extract the roll, pitch and yaw rotations. Angular rates in degrees, which are the rotation in X, Y and Z degrees, which are used in our autonomous surface vehicle for finding the heading angle of the boat. So this is the practical demonstration where the IMU is providing real-time readings in our ROS operating system. As you can see, we are rotating the IMU and it is providing real-time roll, pitch and yaw readings.
So this is the thruster control circuit of a board. The components are a 12-volt LiPo battery, an Arduino for providing the PWM signals, and an ESC for providing the PWM signals from the Arduino to the thruster. And this is the Arduino code, and this is the thruster, which is the TH500 provided by the Blue Robotics company. Now let's show the working of the circuit. So first we are giving the power to the circuit, and then the control signal from the Arduino. So this is the initialization of the thruster. The code is uploaded for running the thrusters for 10 seconds.
So our next sensor is the LiDAR sensor, which stands for light detection and ranging. So it is a industrial grade sensor by Hokyu. So in this sensor, for working this sensor, we are providing it power through Arduino Nano, and it is directly connected to our laptop through robot operating system platform ROS. And the software which we are using for visualizing the map is RVIS platform. So if we can see, if we are placing our hands around the LiDAR, it acts as obstacles, and we can see the map is forming. It's all the white spots are the obstacle around it. If we remove our hands, so it will create the map around. Basically, it is used for obstacle detection and avoidance.
So this is our linear actuator, and we are using it to control the thruster movement of our boat. So let's see the working of it. So as you can see below, the turbine is tilting in the right direction as the linear actuator moves forward. And now the linear actuator is moving backwards and the turbine is moving in the right direction.
So for software purposes, we are using YOLO V5. You only look once, version 5. So for object detection, we are using convolution neural networks that train on various neural networks and that are used to detect objects in the real-time application. And this can be shown in my laptop as there is a real-time detection. This is very good for maneuvering and detecting obstacles and avoiding them.
In conclusion, developing our autonomous flood rescue boat has been both challenging and rewarding. We addressed the need for better flood rescue capabilities, designing a robust boat with advanced sensors, autonomous navigation, and effective propulsion. This journey also taught us valuable lessons in teamwork and leadership. Looking ahead, our focus is on enhancing our autonomous flood rescue boat. We are integrating GPS for real time tracking of stranded individuals, enabling swift and accurate response efforts. Implementing autonomous navigation using LiDAR generated maps will optimize our route planning and obstacle avoidance capabilities. Additionally, we are working on stabilizing our sensors with Delta robots and shock absorbers.